Hello and welcome to this video about convex spherical mirrors. In this video we're going to look at what is a convex spherical mirror, how do we draw ray diagrams for convex mirrors, and what are parabolic mirrors. As you can see from this picture, you are already familiar with convex mirrors when you drive a car. Many of you have seen this sign, objects in mirror closer than they appear. Let's take a look at why that is the case for convex mirrors. So remember, a concave mirror, such as this one right here, converges incoming light. The incoming light converges at the focal point, but a convex mirror diverges the incoming light. If we have incoming light coming here, here is our mirrored surface on the convex mirror. Convex spherical mirror is outwardly curved. The mirrored surface is outwardly curved, and it's also the portion of a sphere that diverges incoming light rays. So when these light rays come in, the light will be divergent. Remember these equations. They also apply to convex spherical mirrors. Remember our magnification equation and our mirror equation. Those will apply to convex spherical mirrors. However, let's walk through how we will draw a ray diagram because the image is a little bit different for a convex mirror. For a convex mirror, we will still draw the same three rays that we did for our concave mirror. However, when we are looking at a convex mirror, the focal point and the center of curvature are going to be on the opposite side of the mirrored part. So they will be on the back of the mirror. You can see here we have our object, here we have our mirrored surface, the front of the mirror. The focal point will be in the back of the mirror, and the center of curvature also is in the back because this came from a spherical shape. We will still maintain the fact that this distance here is going to be called P, and then the distance from the mirror to wherever the object happens to be is still going to be called Q. Lowercase f will represent the focal length, the distance from the mirror to the focal point. That would be right here. And the radius of curvature, capital R, is going to be this distance from the mirror to the center of curvature. So let's look at drawing ray 1. Ray 1 is going to be drawn from the object parallel to the principal axis here to the mirror, and then from the mirror through F. Now this is going to be a dotted line because this is actually not a real light ray here. The light ray is being reflected, much like in our flat mirror. So this will be a dotted line through F. Now how do we draw ray 2? Well, ray 2 is going to be from the object through F, and then from the mirror parallel to the principal axis. How do we draw this? You can see right here, we're drawing ray 2. Of course, this is real light that is traveling here, and this is going to be a dotted line because this is behind the mirrored surface going through F. The second part of that ray will be this reflected ray right here, and that will be reflected parallel to the principal axis from the mirror. That is ray 2. Ray 3 is going to be the same as for concave mirrors. It's from the object through C and then from the mirror back along itself. So let's take a look at that one. That one's represented in blue. We're going from the object to through C. In this case, it's going right here. Again, we make this portion behind the mirror dotted because it's not real light ray, and it will be reflected back again on that same line. At this point, can you see where the image is going to be? The image is going to be the point at which all three of these rays intersect, and you can see that right here. They are all intersecting at that point. So here is our image. Right there, it is upright, it is diminished, and it is definitely a virtual image, not a real image. So you can see that convex spherical mirrors can take objects in a large field of view and produce a small image. So they're very well suited for providing an observer with a complete view of a larger area. A lot of times you see these in busy hallways, monitoring the hallways, or you could see them in car rear view mirrors. You can see a wider field of view with these mirrors. And the warning is necessary because you can see if someone didn't realize it was a convex mirror, they might think it was a flat mirror and think that the image was indeed the same size image as what they were viewing. But because of the diminished size of the image, the object appears to be farther away than it really is. And the value of M for a convex mirror is going to be positive, meaning the orientation of the image with respect to the object will be upright, and the type of image will be virtual. Let's give a little bit of consideration to something called parabolic mirrors. Now, you've probably noticed that certain rays in the ray diagrams do not intersect exactly at the image point. This occurs especially with rays that reflect at the mirror's surface far from the principal axis, such as in this diagram. These are pretty far from the principal axis, and they definitely are not converging right at the focal point. This effect is actually called spherical aberration. It produces a blurred image, and it's present to some extent in any spherical mirror. So a simple way to reduce the effect of spherical aberration is to use a mirror with a very small diameter. If the diameter is really small, then none of the rays are going to be reflected really far away from the principal axis, and it reduces that spherical aberration. However, that's not really useful for certain applications. Telescopes, for example, want to take in as much light as possible, and if we have some mirror that has such a tiny diameter, tiny radius, we can't get as much light in that we would like to get. So there is another option, and it is called a parabolic mirror. A parabolic mirror is a segment of a paraboloid, which is just a three-dimensional parabola with the inner surface that is reflecting. All the rays parallel to the principal axis here, they converge at the focal point regardless of where on the mirror's surface the rays are reflected. And so they will all be converging right at that focal point. Parabolic reflectors are really useful for flashlights, automobile headlights as well. Those are some uses for them in addition to telescopes. If you're looking for an advanced idea, look at how reflecting telescopes specifically use parabolic mirrors. I look forward to seeing what you come up with, and we'll see you in class.